Hi, welcome. Welcome to a little bit more review, and then we're going to move into a new topic today. So this is not going to be on the exam. It will be on the next exam's topic. I decided to change the format a little, so exam will be on Tuesday, and then I'm not going to assign any homework or quiz that week, so it will give you more time to get up to speed with it. The next homework will be a combination of more questions, though. So it will have the op amps and then the other two topics, which will be capacitors and inductors by that time. So don't need to worry about a homework or quiz on the week that you have exams. Does that sound better? Okay, I figured that was probably going to be to your liking. Questions?
It said we have lectures 10 and 11 next week.
Yeah, that was wrong.
Okay.
I saw that too, so I'm working on updating that. So you'll have, this is lecture 8, and then next week we'll have lecture 9 on Thursday, and then there'll be 10 and 11 the next week. They were just off by a week. I haven't formatted those into the week format yet. Other questions? Any questions? Okay. All right, so again, the exam will be next Tuesday. It will be during this time. You are required to be here in person. It will be upstairs in the Engman Lab, Web L210. And you can bring your computer, your laptop, your iPad, your tablet, whatever you use electronically, bring those. Bring whatever you use to scan your information to upload your work. You will need to submit work, otherwise you may not get credit for the exam, so you need to make sure you're submitting your work. It will be considered cheating if you use any artificial intelligence searching. That would be considered cheating if you, and by the way, most of those are not correct anyway, so don't rely on those. But it would be considered cheating, so no any artificial intelligence such as ChatGPT or any of those type of search engines are allowed. No online assistance of any type, and any online communication between individuals is not okay. Circuit simulator is also not okay. So you can use Google search engine, which is, I know. I'm not quite sure how to navigate this yet, but most of the time when I've done searches through there and some of the Copilot stuff comes up, it's inaccurate anyway. So I'm just going to say, yes, you can use the Google search, but no actual like ChatGPT or any other apps like that. And don't rely on the information you get back from even the Google searches, because they're not going to always be accurate. Okay, other questions? Okay, so also bring calculator, or if you use an online calculator, that's also fine too. So it will be pretty much open material. The topics will be the KCL, KVL, Ohm's law, power, equivalent resistances, current voltage dividers, Whetstone bridge, superposition, Thevenin equivalence, and max power transfer. So last time we didn't get to the Whetstone bridge and the power transfer, and so I wanted to just go over what I expect from those for next time before I move on from this material. So Whetstone bridge, if I've given you the source value of 10 volts, and I've told you that resistor 1 is 1K. And this first question part is if I've said you've measured VAB and it comes out as 0 volts. I'm also giving you the R2 was 5K and R3 is 1K. Two questions: what is the R strain value, and what value is VA? And I'll also help you by saying that this is a ground location. All right, again, talk to your neighbors about this question if you would like. And if you haven't met your neighbor, do introduce yourself again to your neighbor. Okay, so if VA is 0, this means that the voltage between here to here has got to be the same. So VAB means that you have VA minus VB. So those two have to be the same if it's equal to 0. So if those are equal to 0, and I already know R1 and R2, I notice that the understanding part of this is that this is a voltage divider and this is a voltage divider. So if I identify that they're voltage dividers, I can find the value of VA or the value of VB, knowing the resistances. So with that, then if VAB equals 0, that means that those have to be equal, so R strain would have to be R2. So that's how you get to R strain is equal to R2. And then the value of VA is going to be the division between R1 and R2. And with my ground on the bottom, it's going to be across R2. So my voltage divider there would be V source times R2 over R1 plus R2. So in this case, it would be 10 times 5K over 6K. $50 over 6. I just went blank. What's 50 over 6? Whatever 50 is. Okay, 50 over 6. I'm leaving it in that. Okay, we'll leave it in fraction form. 50 over 6 volts would be your VA value. So if the V source changed to 5 volts, so that just means that if this source went from 10 volts to 5 volts, what value do you have for R strain now? Same. There's no change, right? That voltage doesn't affect the resistance value. What affects the resistance values are the other resistor values in this case. So this is gonna just still be our strain is R2. No change. Okay, so then the second question was asking, like, what would I need to do is if I didn't have those conditions and I have R2 is 1K. So if this was 1K and this is 1K, put it in red. Well, okay, if both those are known, 1K and 1K, is there something I could do easily to measure R strain? Any ideas?
Photography still on?
You could set it to 1. If you set it to 1, then what do you do? So if I set that to 1K,
Do the opposite of what you did in the first one.
then our strain would just be 1K. So you can measure it from there. So that one again is alluding to the resistors are changing your R strain value, not your voltage. So those are kind of some of the questions you can expect instead of like having to put all the values into the formula of the derivation of the R4 equation that you did in the homework. So that was in the homework instead.
Should we always expect VAB to be 0?
I mean, I could ask you, like, set it to there, and then what would our strain be if these are the conditions?
Does it still only rely on the resistors?
Uh-huh. Yep. I could ask you also, this could be a voltage divider question, in that what is the value at VA? That's a voltage divider question. Okay. All right. Yes.
So VAB is just VA minus VB.
Uh-huh. So whenever you see voltages or subscripts that are a combination of locations in a circuit, it is taking the first one, subtracting off the second one. So that's where the VAB is a subscript, so VA minus VB. And that's kind of terminology for electrical circuits, so as you see that.
So when you're trying to find VA, is it just like the current through that left side of the thing times the resistors?
Uh-huh. Yep. So if I don't see that it's a voltage divider, I do note that this is a branch because that A is just a wire to measure it. So it's going to be the same current because I have an extraordinary node on the top. Guess I should fill this hole in. This is all in. Sorry, meant to do node. Okay, so there's your node, that extraordinary node. And then you have an extraordinary node on the bottom. Oops, green. So 2 extraordinary nodes, and then the branches are in between them have 1 current.
Do you not have to do like the voltage going, like to find the voltage at A, do you not have to do like the total voltage minus the amount lost in R1?
So your pathway, you could take 2 different pathways. So from A, you could go down here to ground through R2, or you could go this pathway to ground through the V source minus the voltage drop across the R4. And those would be equal at VA. Does that make sense? So if you found the voltage across R1, you would still have to take the source minus that. Because you have to take the full pathway back to ground. So V2 would be is easier, so that's why I took that pathway across there and did the voltage divider across that one instead. So remember that voltage divider is just the voltage across that one resistor. All right, other questions? Yes.
If VAB is always equal to 0, or if VAB equals 0, is R1 and R3 always equivalent? R2 and strain gauge always equivalent?
So again, it depends on like if R1 and R3 are equal, then the bottom ones would be equal. But if R1 and R3, which are the top ones, are different, it would be the ratios.
Gotcha. Okay.
And again, you did that in your homework. Okay, does that make sense? That one was more algebra than anything. Yes.
So for the bottom half of the question then, so VA 5 was then, so resource times if R2 is now 1K, or what if R2 is 1K?
So you're saying in this case, if R1 equals R2 equals R3 equals R strain
Yeah.
equals 1K, then yeah, your output would be 10 times 1K over 2K. So VA and VB would both be equal to that of 5 volts. Was that your question?
Yeah.
Yep, so that would be equal to 5 volts if that was the conditions. Okay, other questions? Clear what I would expect from a whetstone bridge question? Okay. All right, maximum power transfer. Oh, I have an extra page in here. Okay, last time we found the Thevenin of this circuit, and the Thevenin was a 5 volts for the voltage source, Thevenin, or the VTH portion, and then your RTH was 2.6K. So VTH was found as 5 volts and RTH of 2.6 volts, 2.6K ohms. I cannot talk today, I guess. Okay, so if this is the case, and we wanted to put a load resistor on here, what load resistance will produce maximum power transfer?
I added 3 and 5 in series. There's a third resistor. You're turning that here.
Okay, so yes, you guys are correct. All of this is to say, well, it's going to be equal to the RTH. So you just look at the RTH value, and remember that max load, we took the derivative with relation to RL of the equation, and that gave us, it just needs to be equal. So if RL equals RTH, then you're at max. So RL in this case would be 2.6K. And that's all you need to know for the max power transfer. Until you go put a speaker on there, on your system. All right, any questions about that? Alrighty. Okay, that concludes the material that you need for the first exam. Any other general questions about the first exam material? Yes? Nope. Just Thevenin, so focus again on Thevenin only. All right, other questions? Okay, we're going to jump into the next material. So remember the RoboBees, and is there any questions? Okay, remember the RoboBees. I keep going back to this one, but it's a fun little application. So on the RoboBees, there's the antenna, and the antenna needs to bring in some information. It is a very small amount of change, though. So what we want to do is what we call an amplification of that signal. So if it's a small voltage, we want to amplify that voltage. Instead of 0.000001, we want to have a 1 volt or something that's a lot higher, so we can work with that number versus a 0.000001 value. Which is harder, and you get more errors with it. So we want to create a circuit that amplifies this signal. So what we get to a device that actually does that, it's called an operational amplifier. Another application is that you internally, when you have a pacemaker, you do not want to have a lot of voltage going on in your body. So they will use a very low power and low signal, and then they'll transfer it to an external device on the outside of the body, and then you want to amplify it once you get that information. And so it's being amplified and given more power outside the body versus inside the body. So that's what a pacemaker actually does. Then you have like distance antennas that by the time the signal gets somewhere, it's lost all of this power to it, and it's received, and it's a very low number. And again, you want to amplify that number back up to a high number, try and remove all the errors from it, and then send it on. Yes?
When you have something that's further away, does the amplification need to be greater? Does like the amplification change with distance?
Yeah, so you guys are too young to know, but like we used to have to travel, like all the signals went through wires themselves, physical transmission. So the very first internet was actually built here between the University of Utah and in California. And so they built the physical wires from here to there. And then they started doing them over, so they buried some, but then a lot of them they were using the power cable lines to transmit, but physical transmission across things. And so as we would then turn to wireless, we started getting the cell phone. And so the cell phones, if any of you have heard, like you keep hearing about towers being put up. What those towers do is they create the smaller distance physically between the communication lines. So when your phone actually sends the signal, it used to be huge. And now because we have less distance to have to travel, that's how cell phones have also gotten to be smaller in technology size too, because they haven't needed as much power to actually get there. So yes, you used to need a lot more power to transmit for in a farther distance. All right, other questions? This is a great topic for your final project too, if you want. Okay. All right, so as I said, there's actually a device that's called an operational amplifier that actually will amplify a signal as it's put into this. This is the internal parts of an operational amplifier. These are called transistors that work as what we call a switch. So they act as a switch to connect different locations. And they actually can amplify the signal. We're not going to get into the details of how they amplify. If you have interest in that, then you can take our follow-on course called ECE 2280, where you actually learn how to build these amplifiers. But in here, you don't need to know much except for this is kind of a black box, how you're going to put your inputs in and what happens to it on the output. So that's what I'm going to expect from you guys. What you do is you configure this operational amplifier by connecting it with external components. So in the lab, you're actually going to be using these. You guys haven't yet, right? Used the op-amps yet. You are going to use these op-amps. And so what you're going to get is a chip that's like this. And so on the chip, there is this little divot in the packaging. I don't know if you can see that, but it's a little divot in that it identifies the top of the chip. So this is where you know it's the top. When you then look at a data sheet, this will be the top so you can orient the pins in the correct way. This would be your pin 1, pin 2, and you go down. And then it depends on the data sheet whether you label this pin, let's see, 1, 2, 3, 4, 5, 6, 7, so pin 7. Eight, 9, 10, 11, 12, 13, 14. Okay, so you have to check the data sheet to know what pin this is. Some of them go down and then go back up as 8. Some of them go down and then relabel them. Most of the time, it's going to be the pin 8, and they go down and up. But you do want to check your data sheet for whatever number the chip is. This one would be an LM324. And then you would look up a data sheet for LM324 and look for that actual physical diagram of the pins. As mechanical engineers, I'm sure this will look more familiar to you when you look at these data sheets. For electrical engineers, they're like, I have to look for what? So you guys have a different strength than electrical engineers do. But do look on the data sheet to verify for your particular chip number. They do change that sometimes in the stock room, so do make sure you look at that. So that's how you know the configuration of how you're going to put it into your breadboard. Then you need to know what pins are what in there. So there's going to be a positive supply that you need to put on the chip. And in this case, that one is located here at plus VS. And then you need to know the negative supply of the chip. And then in this one, this is going to be the negative VS. Make sure you hook up power to your chip, else it won't work. So hook up power, or connect, I should say connect powers. Else it will not work. So you need to connect power to your chip. And then from there, you can determine these 3 areas. So one is going to be a plus input, one is going to be the negative input, and then you're going to have an output pin. So we'll talk about what to connect to the plus and the negative, but just make sure you identify what pins are going to be your inputs and your outputs. So 2 inputs. So it will have 2 inputs and then it has 1 output. Okay? Any questions about what it kind of looks like? So it's going to look like this weird symbol. It's just a triangular symbol. Again, you don't need to worry about what's inside it, just that you have 2 inputs and 1 output, and then how do you hook it up on the breadboard itself. All right, so now let's kind of talk about how it works. So how it works is internally, with connecting it to power, we're going to use the draw of that power. And so the voltage source is going to take the plus side and take off the negative side, and then multiply it by this internal gain. So, for example, if you have 3 volts on that plus side, ground on the other side, and I've connected it to a plus and a minus 10 volts, plus on the plus side of 10 volts, negative supply of minus 10 volts. My V out is going to be a gain value, A naught, 3 minus 0. Typically this is really large. And so out of this, at maximum, I can only get 10 volts out. So in this condition, I would see 10 volts out because it can't go beyond 10 volts. So it will hit maximum supply plus supply. So in this case, it would give me the 10 volts. If I put in negative 3 volts, what do you think I would get out of here? Correct. I would get out negative 10 volts, correct. Okay. Let me do another one. What if I put 0 volts on the positive side and I hook this up to plus 3 volts? What am I going to get out? I'm going to get out negative 10 volts. So it would be 0 minus 3, and then it would be, so 0 minus 3 times the gain, and that's still a negative 3, a very large negative number. So that would limit it to negative 10 volts. If I put on, do one more. Still 0 volts and negative 3 volts. What do I get out here? I get a plus 10 volts. Okay? So this is called a comparator. And this is one way to operate with an op amp. So this is one of the easier ways. There's no connection from the output back to the input. Yes?
What's A naught again?
It's a high gain. So that's called a gain, internal gain.
Will we be given a value for that?
It's just really high. And it doesn't matter what it is because this will still always operate higher. So minimum's
By really high.
like 1,000. So 1,000 times 3 would be 3,000 volts. And you can't have that, so it maxes out of what the supply is. So 3,000 instead, it can't physically do that, so it gives you the limit of the highest positive, which is 10 volts.
Okay. So you just can't exceed those values
On the supplies. Correct. So those supplies are like a battery, so you can't get out higher than you have for your batteries. You can put them different. So you can have 10 volts to ground, and then your lowest value out would be ground. Yeah. You wouldn't be able to get below that. You can't get a negative value. Or you could do the other way. You could do 0 and minus 10, and then only have negative values out. And then 0 would be your highest. Mhm. Yep. All right, other questions?
How do you keep the signal when it always just puts it at the highest or the lowest value?
So we're going to talk about that next. So it's a different configuration. So this is only if I want to know, like I want to compare values. So that's why we call it a comparator. So comparing between the two values. So I did to ground to give it, it's easier to 0 and that. But you could have 3 volts and you could have 1 volt. And then a plus 10 is going to tell you that the plus side was higher than the negative side. And then the opposite when you have like, oh, I had 3 volts on the negative and a plus 1 on the positive, my negative still is higher, so it will give me negative 10 out. So it gives me an amplification, but it just tells me which one was higher. It doesn't give me the exact difference, which is more what you were asking. So if we do want to get like, well, we do want a difference, or we want to amplify an AC signal which has varying values in it, then we would go to it's weird, a different configuration. So this is also can be called a switch, comparator or switch. Would be another word you would hear here, which is it just kind of gives you an on or off kind of information. So what we want to know from the op amp is to being able to identify what kind of configuration do we have. Do we have a switch or a comparator, or do we have the other configurations that I'm going to show you, which is going to be there's inverting, non-inverting, voltage follower buffer, inverting summer, difference or subtracting, and non-inverting summer. So those are the different configurations. So the first thing you have to do is, do I have a switch or comparator, or do I have something that's called feedback? If I have feedback, then that would be one of these configurations. So here are your different configurations. So how do you identify if it is a switch comparator versus a feedback? So this one is called a non-inverting amplifier. And here I see my output node, and then I see that there is a pathway that goes back to back to the input. And it goes into the negative one. So the ones that go into the negative side are always going to be stable. Those that go into the positive are not. So if you go on to, I think for you guys, MEEN, the classical control system, which is 5200, you'll get into the stability portion of a circuit like this. We're only going to look at stable circuits, and so these will always, if there's a tie back as far as a pathway, so not a node, but a pathway back from an output node back into the input, it would be feedback. So up here, you can see that there's no pathway from the output back to the input. So these are going to just be a comparator and switch. So this is a comparator switch. So first you identify, is it feedback or not feedback? If it's not feedback, then it would be a comparator switch. If it is feedback, a non-inverting amp has the input signal. So you first have to identify input signals. So one, switch or comparator or feedback. And then locate input or inputs. So if feedback, then locate inputs or input. And then which, I'll put an A. Okay. If one input you only have three options: non-inverting, inverting, or a follower, which is also called a buffer. If just going to write over this. If you have two or more, you're going to have a summer circuit. So it will either be inverting, non-inverting, or difference summer. So there's three of them. I guess I'll write them all. So inverting summer, non-inverting summer. Or it's called a difference amp. So with these, you're trying to narrow down, like, is it this or this one? If it's this one, great, I'm done. If it's not, then I need to look at the inputs. If I have one input, it's got three options. If I have two or more, it's got three options. And then from there, you're going to look at what input location. So in this one, you look at it, is this a switch or comparator or feedback? It's feedback because you have a pathway from the output back through to an input. So you identify its feedback. Then you have to identify the input. It's going to be on the left side, or where the plus and the minus is on this. In this case, it's on the left, and this would be my input. So I have one input, and then I have to look at the location where that input is going into. It's going into the plus side, so that's going to give me a non-inverting amp. In comparison, the inverting amp has feedback also. So I see that there's a pathway there to get back to my input. And then I need to identify the input, and that is here. And then the input goes into the negative side. So this one is called an inverting amp. Okay? Then the third option for a single input is the voltage follower, which is this one. Again, I can see that I have a pathway from output back to my input, so feedback. I identify my input, which is Vs, and this goes into the plus, but there's no resistor. Or I should say no pathway to ground. So with a voltage follower, there's only the pathway directly to the negative, and there's not going to be another pathway also that goes to ground. So what I mean by that is here I have a pathway to ground from the output, and here I also have a pathway to the source. I should say source or ground. To ground or source. So it only has a single pathway just right back to the negative input. That's the follower. So those are my three options for single input. So again, switch comparator or feedback. If it's feedback, how many inputs do I have? If I have one, I have three options: inverting amplifier, non-inverting, and voltage follower. And then you have to look at the differences between the three. Does that make sense? Okay, so then the next one is, well, what if I have more than one input? So in this case, I look at this amplifier. I see, yes, it's got connection through here back to the input, so feedback. I have 1, 2, three inputs here. So it's got to be inverting summer, non-inverting summer, or difference. I look at where it goes in. It goes into the negative terminal. So this is going to be an inverting summer. So the negative for inverting summer. So that's my inverting summer. All right. I've got a pathway again, output back to the negative input. So it's got to be feedback. Where are my inputs? I have V1 here and V2 here. V1 pathway goes into the negative side. V2 pathway goes into the plus side. When I have them going into the different inputs, this is called the subtracting or difference amplifier. Yes?
Can the difference be inverting or non-inverting?
What do you mean?
Like, is it an inverting difference one, or is it like a
So it's
non-inverting difference one?
it's always going to take, so if you think about superposition, and if I removed the V2 and grounded that one, you actually get an inverting amplifier. And so your V1 gives you an inversion, so it's a subtracting off the negative side. And then the positive one, if I was to ground the V1, it actually is, the signal comes into the plus side, so it's a non-inverting amp. And then you can add up those results to get the difference. So you're always going to have whatever's on the positive side actually be the plus portion, and then the negative is going to be subtracted off of it.
Yes.
Does that make sense?
Yes.
Okay. Okay, and then, okay, so here we have again, last type of amplifier. So I see a pathway goes back to the input, so I have feedback. And then here, these are written out instead of just as a dot, they're written out with the source themselves. And so those would be my two inputs. So it's got to be inverting summer, non-inverting summer, or difference. And then both of these signals go into the plus. So these are non-inverting summing, or non-inverting summer. Does that make sense? Okay, so first step is to being able to identify these. Don't worry about how they actually amplify and what the result is out of them yet. We'll talk about that next time. But I want you to practice identifying these. So we're going to do some practice. Okay, what's this one? Correct, switch comparator. What about this one? Correct, non-inverting. Good job. So I identify where it is and it goes into the plus, so non-inverting. This one? There's my source, it goes into the negative, inverting. All right, this one? Non-inverting summer. So my two inputs, and it goes in there. All right, what about this one? Inverting summer. All right, this one? Good job. Subtraction. All right, so two sources, and then they go into the opposite ones. All right, this one? Correct, buffer follower. All right, these are a little easier to identify when they're just by themselves. So it gets more complicated when you actually are like in a circuit, so. Okay, what about this one? Correct. I heard several people saying it. Good job. Non-inverting. So here's my input, and it goes in here. And first I identified that add feedback. So it's written a little differently. So even though you have a resistor, the signal still goes into that plus side. So non-inverting amp. This one? Some of you are pretty quick. Good job. Inverting. So there's your input, and it goes into the negative side, just one input in. So inverting. Power. So VCC is going to be, this will be your power, so you can ignore it. And I forgot to say, if on the other ones, they're not drawn, so it's implied that they have power supplies to them. So when you don't see them drawn, still know like there's got to be a plus and a minus power going to them to power them. So most of the time you will not see them drawn on a schematic, but you have to imply that they are there. So hint, this will be my source. And correct, it would be non-inverting. This one? That's your hint. Correct, inverting. So that is a pathway to the negative side. So it would be inverting. This one? Hint. Hearing some of you. Non-inverting. So I heard a buffer. So note though, with a buffer, it has to just have one pathway back, but this also has a pathway to ground. So because it has a pathway to ground, it's not a buffer. And then it only has the one input, so it's going to be non-inverting. Yes?
So the 20 km to ground doesn't count as an input?
So what happens is it gives you, so I forgot to say this, but part of the characteristics when we go to actually solve these will be that there's no current drawn into the inputs. So that current has zero current in there. So all your current here flows through the 5K and then will flow through here. And that actually gives you one current in the branch. And so the I times the R across that gives you another input or a different voltage at VS prime. So this will be the voltage that actually goes into the circuit and gets amplified. So it will be a smaller value than your original value of VS. And it actually is more of a voltage divider there. Does that make sense?
So would it be a summer if like the ground was like a different V?
So it would be a summer if you had another input that was connected at that plus. So as you see in here, they join, so they have a joint connection here before they go into the op amp. Does that make sense? So it would be only if you had another signal. But just because it's dividing it, it's still just one input. So just a non-inverting amp. Okay. Other questions? Yes.
Can you explain again what a buffer is?
So a buffer has just a pathway back to the negative side. So it can have a resistor in that pathway, but it just can't have a pathway to either ground or back to the source. So in this case, it has just the single pathway, but there could be resistors in here. I could add a resistor here. I could have multiple resistors in that pathway, and it'd still be a buffer. It's not a buffer once I have a connection from here to ground. Then that would become a non-inverting amp.
Okay.
Does that make sense?
Yeah.
All right, other questions? All right, let's look at a few more. This one. Sorry. You're correct, non-inverting. Did that one? What about this one? So one source going to two locations. So this one would be a difference, subtracting. So it's taking different ratios of that and subtracting them. So even though it's one value of source, it still is at two different locations. So it looks like two different inputs. Does that make sense? Seeing some yes, some no. Some blank looks still. Okay. All right, what about this one? I just like lose my whole. I think the system just turned off. That was weird. Okay. Okay, sorry. Little technical glitch there. Okay, so this one we have to look a little closer at kind of what is going on. So on this wire, I have a plus VS. Fell there. And then that pathway goes into the negative side. And then on this side, I have a negative of the VS, which also goes into the negative side. But what I see here is that the plus side of the op amp goes to ground. So there's only input that's going into the negative side.
Yeah.
So this pathway here is just, that node is all 0 volts because it's tied to ground. So there's 0 volts or ground, or you would look at it as ground there. And so this would be an inverting amp. All right, questions about that one still? So what would you have to do different to make this into a different ZAMP? So instead of doing ground here, you would have to have a connection to one of those sources. So if I didn't have ground and I instead did a voltage divider there. Yes.
There's like no current going through R2 and R3. Those are just like there, but there's no current going through.
So there'll be current going through them as you have a positive VS. So the plus VS will actually give you, if you have an alternating signal on here. So think about this as more of a sinusoid and not a fixed value. So for a plus value, yes, you would have current there and then no current going through the R1 and R3. Yeah. Yep. Okay. Okay, I don't think I want to jump into this one yet. So we'll do this one next time. Any questions about the material we've covered today? Okay, yes.
The power to power the inverter, is there a voltage drop if, like, for the separate circuit that powers the?
So what actually happens is on a data sheet, it will say like your max voltage, if you put in 10 volts, is like whatever you apply minus 2 volts or something. And so it's actually going to be less than what you actually put into it. Does that answer your question, or did you have a different question? Okay. So instead of being 10 volts out, you would actually get 8 volts out. So it does consume some power in there. And then the data sheet tells you how much power it will consume. All right, any other questions? Okay, again, make sure you're ready for the exam on Tuesday and meet up in the Ingman lab.